So in the last two classes, we were now looking at our electromagnetic wave propagation in the lossy media. So where we have seen that, when sigma is not equal to 0 for our medium, in that case, it will incur an attenuation to our electromagnetic wave. And we have looked at the 1D scalar wave equation, and we looked at its solution, and we saw that this extra term will not exist along with the amplitude of the wave, and this term is responsible for attenuation. And gamma is the propagation constant, where it is made up of the real and the imaginary part. The real part is called as the attenuation constant, and the imaginary part is your phase constant. And we have seen that when sigma becomes 0, then we go back to our lossless medium. Okay, we go back to our lossless medium. And now we also looked at our alpha and beta values, which are these, and then the intrinsic impedance. And then we looked at our loss tangent, and we looked at how loss tangent can change the behavior of a material from a good conductor to a good dielectric. So we have identified omega, which is frequency of operation, as fourth parameter which defines the characteristics of a material, besides the permittivity, permeability, and the conductivity. And we took an example. So this is the example of our electromagnetic wave in the lossy medium. Okay, I think this is where we stop. So now, we also looked at the skin depth. So we defined the skin depth that is based on, how the wave is attenuating, and the skin depth is 1 over alpha. And we have seen that skin depth is nothing but the distance over which our amplitude of the wave decays to 1 over E, which is 37%. And we took this example and we stopped. Okay. So now today we will look at the classification of the materials. And if you see here, these are the 1, 2, 3, 4, 5 different classification of materials based on the sigma over omega epsilon value, that is based on the loss tangent. As a perfect dielectric or a lossless dielectric, then we have lossless, low loss dielectric, then we have lossy dielectric, good conductors, and perfect conductors. Now here what we were doing was, we were not trying to look at this case. We were trying to look at this case, the good conductor case, and then we were trying to just simplify the alpha and the beta expressions for the good conductor. So because we know for the good conductor, the sigma over omega epsilon is very much greater than 1. So looking at taking this idea, what we were doing here is we were now looking at our alpha and our beta expression. And as you can see here, so this is the assumptions we are making. First is this term. So this term has sigma over omega epsilon. So this term is very much greater than 1. So therefore, we are neglecting this term. Similarly, here also we are neglecting this term. And then now what you can do is, from these two, you can take sigma over omega epsilon common, and you can take it outside. So this is a root here, and this is a square. So root and square cancels. When it comes outside, it will be just sigma over omega epsilon. And the inside bracket will become 1 over sigma over omega epsilon square plus 1 under root. And this term is very much greater than 1. So therefore, this term will be very much less than 1. Again, it can be neglected. Oh, sorry, this I should not use it as 0. I should see just neglected. So this is neglected. And therefore, here also this term will be neglected. And therefore, root of 1 will be 1. And that's why you will see that my alpha is now simplified to this expression. And beta is also simplified to this expression. So which is omega root of mu epsilon over 2 times sigma over omega epsilon, which is simplified to root of omega mu sigma over 2. So this is my alpha and beta, which will be the same. This is only for good conductors, guys. So therefore, for any problem that you have, you can first identify whether it's a good conductor or not. And if it is a good conductor, then you can use the simplified expressions rather than using this, bigger expressions. In a similar manner, we can also simplify the intrinsic impedance. So intrinsic impedance is this one. So therefore, when you simplify it, you will see that the intrinsic impedance will be this one, which is root of omega mu over sigma times root of e power j 90. That is root of omega mu over sigma e power j 45. Okay, e power j 45. That is, the good conductors will give yes, Mr. Abdul Rahman Al Mushrif, can you tell me? Mr. Yes. Abdul Rahman Al Mushrif, yeah, looking at this, can you tell me? So the good conductors will give how much phase shift between our electric and magnetic field?
It's 45.
45. So this is the 45 degrees. It will give you the maximum phase shift, which is 45 degrees between the electric field and the magnetic field of a propagating transverse electromagnetic wave. And this is for the good conductors. This is for the good conductors. And if you remember in the last lecture, we saw that this is the value sigma over omega epsilon, and this sigma over omega epsilon is related to the angle eta, and this will take values between 0 and 45, right? So therefore, good conductors will give us almost the maximum value of the phase shift, which is 45 degrees. So now let's take an example. So here you have an electromagnetic wave which is propagating, and this is the frequency of the electromagnetic wave, and these are the characteristics of the medium. It is a non-magnetic, mu r is 1. This is the relative permittivity or the dielectric constant, and this is the conductivity of the material. Now we need to find, the electric field is given as this one. So if you see the electric field is given in the phasor form. So which is AX 2 e power minus alpha y e power minus j beta y. So now looking at the electric field, Mr. Ibrahim Al-Shamisi, can you tell me what is the propagation, in which direction our electromagnetic wave is propagating?
In the direction of AX.
Yeah, so look at this and then let's see what is the direction of propagation.
X-axis.
No, not x-axis. X-axis is here, right? That means your electric field has the component in the x direction. Okay, but what will be the direction of propagation? For the direction of propagation, you will see cos of omega t minus beta z, right? So you will look at the argument, right? Ibrahim, you will look at the argument. It will be E naught. This is the argument. But now we don't have in the time domain. We have in the phasor domain. No problem. Look at this. This will tell you.
In y-axis, sir?
Yes, it will be the y-axis. It will be the y-axis. You have to look at this one. Because if you convert this into the time domain, then what you will get? You have to multiply this with e power j omega t, right? And then take the real part of this. which will be equal to AX 2 e power minus alpha z cosine of omega t minus beta y. Right? Oh, sorry, not alpha z, alpha y. I couldn't see. That's why, sorry. So it is e power minus alpha y. Now from here you're able to see it that this is 1. See, first it is negative, so therefore it should go in the positive direction, and then it is y, so it is positive y direction. This is the direction of propagation. Okay, so now we will go and we will find all these parameters: the loss tangent, alpha, beta, skin depth, the wavelength, the phase velocity, eta, and the associated magnetic field in the phasor form, as well as in the time domain, which is the instantaneous form. So first, let's find the loss tangent, because this is the first step that we need to do to check how is our material, whether, in which category the material will fall. So this is our first step. So that's why first I'm finding sigma over j omega, sigma and omega and epsilon, all of them I'm substituting, and I'm seeing that it is 180. So 180 is greater than 10, right? So for the good conductor, if you see the sigma over j omega, now where it is, yeah, the sigma over j omega should be greater than 10 and less than infinity. So therefore it falls in this category. So therefore my medium is a good conductor. And now I can use the simplified expressions. So therefore your alpha is root of omega mu sigma over 2. So therefore it is 8.89 Nepers per meter. Beta will be same as alpha, which is 8.89 radians per meter. Skin depth is 1 over alpha, which is 0.113 meters. So that means if your electromagnetic wave travels to 100.113 meters into this medium, then its amplitude will come down to 37%. Then this is lambda, which is 2 pi over beta, 0.707 meters. Phase velocity, omega over meta, and you have substituted here. Then you have eta, simplified expression, root of omega mu over sigma e power j 45. So put all the values here. It is 12.57 ohms e power j 45 degrees. And then what will be your HS, the associated HS? Yes, if this is my this is my electric field, which is in the X direction and propagating in the Y direction. So here again, we follow the same, our idea that we have been using in the last 2 classes. Okay, maybe say Zuhair, can you tell me how do you find? Because if our electric field is in the AX direction and our propagation is in the Y direction, which is AY. So can you help me finding the component of the magnetic field? So how we can find, Zuhair?
Yeah, doctor. As we learned, the propagation, the direction of the propagation is the same in the Y direction.
Okay.
But what is it?
The components.
Yeah, the components. The direction of the magnetic field will be the lost dimension. We don't have X, Y in E. We don't have Z in E. So the direction will be AZ in this magnetic field.
Yeah, direction will be the AZ, but whether it will be positive AZ or negative AZ, how do we identify this? Remember,
by cross product.
Yeah, so we have to get it from the cross product. So guys, just a recall, you have to get it from the cross product. So E cross H is the direction of propagation. So as Zuhair said, this is AY and this is AX then definitely this is AZ. Now to find whether it is positive or negative, you need to go for the cross product. So it should be negative. So AX cross minus AZ will give you AY. And that's why if you see here, I have included minus AZ. And then what is this? This is your electric field E over eta, because we know this is the expression. So put the eta here, and now you just simplify this. So this angle you bring it upstairs. So this 2 over 12.57 will give you this. E power minus 8.89y will be as it is. When this angle goes up, it will be inside our exponential. So e power minus j 8.89y minus j 45. Now in the instantaneous form, multiply by e power j omega t, and then take the real part of this. So you will get this. This will be cosine 40 pi 10 to the power of 60, which is my omega, minus 8.89y minus 45. So therefore, if you see, your magnetic field and electric field is phase shifted by 90 degrees. And this phase shift is because of the material causing, because of the material conductivity. Okay. So you have one more example here. So here you have a plane wave propagating through a medium with, this is the medium parameters, epsilon r is 8. Now it is a magnetic material because mu r is 2. And this is the electric field. And now we need to find the phase constant. We need to find the loss tangent. We need to find the wave impedance, and we need to find the wave velocity. Okay. So again, how can I find alpha first? Very straightforward. Look at this. So here, if you compare this with the standard expression, we know that it is E naught e power minus z over delta, right? So from here, if I compare, I can easily say that my delta is 3. And therefore, my alpha is 1 over delta, which is 0.33 nepers per meter. Okay. Now, the second thing, if you notice, is we need to be careful here because your electric field is in sine, not cosine. So, but when we do the comparison, we always need to go for our cosine. So, what we need to do first, we need to first find the beta, and then we need to find our loss tangent. Okay, because we really don't know what is this medium. Is this medium a good conductor, or is this medium a lossy dielectric? So therefore, first we need to find sigma over omega epsilon. But if you see here from our from the information given in the question, we cannot find the loss tangent directly. But what we can do is you can find it from alpha. So once we know alpha, now can I put alpha and equate it with its general expression? So this is the general expression. See, I'm not using the simplified expression because I don't know the type of material. That's why I'm using the general expression. And this alpha, I'm putting this alpha here. Omega is known to me. See here, from here, omega is known to me. So I'm putting the omega. And now from here, I can easily get the sigma over omega. So from here, when I see I'm getting sigma over omega epsilon, which is 0.5154. So this means if it is 0.5154, so where it is in this region. See, so it is in this region, 5154. That means it lies between the low loss dielectric and good conductor. That means it's a lossy dielectric. So therefore, I cannot use any simplified expression. So I have to use the complete generalized expressions. And this is what I'm doing. So that's why I'm using the complete expression of beta, and I'm finding beta. Then I'm finding the loss tangent, and it is asked to find eta. So I'm using the generalized expression of eta. and then I'm finding the u, which is the phase velocity. Okay, so this is how you need to approach problems which has which has a medium which is unknown. So you need to first identify whether it is a lossy or lossless. Okay, so now we go to the next part, which is the electromagnetic power. But before that, let's take a couple of say poll questions. Again, very simple poll questions. Okay, so here is the next one. Okay, so 40 seconds. So it says that for a transverse electromagnetic wave, the amplitudes of the electric field and the associated magnetic field is related by. So you have 20 more seconds because I'm giving 40 seconds. 10 seconds. 5, 4, 3, 2, 1, and that's it. Wow. This is the first time that I am seeing such kind of results. See, they are all scattered. So see, it says a transverse electromagnetic wave, and I'm talking about the amplitudes, guys. The amplitudes of the electric field and the associated magnetic field. So they are related by what? The amplitudes. Yes, to whom should I ask? Okay, maybe Mr. Muhammad Al-Humedan.
Yes, lecture.
Yes, you tell me the
I think-
amplitudes.
I think the impedance.
Yes, yes, you're right. It is the impedance. Just now we did the example, right? Just now we did this example. Where is this example? See here, the amplitude of the electric field divided by eta will give me the amplitude of the magnetic field. I'm talking only about the amplitude, guys. I'm not talking about anything else. So it is related or with eta, because eta is the ex over hy. But if you see, it is the amplitudes of ex over hy. Okay, so where was I? So stop sharing results. Okay, next one. Okay, this is also very straightforward. So the following are the properties of the electric and our associated magnetic field, which is our transverse electromagnetic wave, and it is propagating in a lossless medium. Okay, but which of them is not correct? So I'm giving more time here. I'm giving another 30 seconds here. $20 seconds more. $15 seconds more. 5, 4, 3, 2, 1, and that's it. In fact, I gave more than a minute here. So which one is incorrect? Okay, so let's share the results. Which one is incorrect? Again. Propagate in the same direction. Is it incorrect, guys? Because this is This is the majority of the students saying. Maybe Abdul Mohsin, you're here?
Yes, doctor.
You tell me, Mr. Abdul Mohsin.
I
Transverse electromagnetic wave. So which one is incorrect? So
I
the
see.
E electric field and the magnetic field both will have. So will they propagate in the same direction?
No, it's with different phase velocity. It's
Oh.
correct in the same direction.
Yeah, it's correct. Yes. With different phase velocity.
Yes.
Yeah, this is the correct one because they will travel with the same phase velocity. They propagate with the same phase constant. Yes. They propagate with the same phase constant beta. Propagate with different field amplitudes. Yes, because this depends on the intrinsic impedance. So this is also correct. This is also correct. This is also correct. Now, they propagate with the phase velocity. They propagate with the same phase velocity. This is correct. But here it is written they propagate with a different phase velocity. So this is the only thing which is incorrect. And this again, we did this right in this example. If you see here, if you compare this with our electric field E0, although it's a lossless case, but still we can make a fair comparison because my electric field is AX. It is 2 e power minus 8.89y cosine of 40 pi 10 to the power of 60 minus 8.89y. So let us compare them. Are they traveling with the same phase constant? Yes. Are they traveling with the same direction? Yes. See, minus y, minus y. Are they traveling with different amplitudes? Yes. Right? And what else was the question?
Phase velocity.
Phase velocity. Yes. So phase velocity is what? U is omega over beta. So if omega is the same, beta is the same, then the phase velocity will also be the same. This is the important properties of our electromagnetic wave, which is the transverse electromagnetic wave. And we did this just now. So anyways, guys, I know, things are, a little bit difficult because now you are put in more pressure because of the reduction in the academic calendar, although the calendar is not available, but still we are aware that it might happen. So, do your best, try to do a proper time management, and believe me, from my experience of teaching EE340, the chapters of electromagnetic waves, I believe they are easier than your electrostatics and magnetostatics. They are easier. Whatever we are talking about, the wave equation and the solution of the wave equations and other things, we are looking at the examples. The examples are not that difficult. And this will be the same case even when it goes to the applications as well. Okay, so please start practicing. Okay, so now let's come back to our lecture. And so now we are now looking at our electromagnetic power. Okay, and we are starting with a very simple argument. So what we are saying, if my electric field and magnetic field, they are traveling in the same direction, the direction of propagation is the same, because my electric field cross magnetic fields points to the direction of propagation. Okay, and my electric field and magnetic field, they are coupled and they are say going together, and my electric field what is the amplitude, what is the unit of my electric field is volts per meter, right? And what is the unit of my magnetic field is amperes per meter. And if you combine them, you are seeing that it's watts per meter square. That is nothing but power density. So this is highlighting that your electric field and magnetic field together are actually carrying power together in the direction of propagation, power density. And that's why this E cross H, which till now we said that it's a direction of propagation, is actually called as a pointing vector. It is called as a pointing vector because it is indeed, it is carrying both of them. E cross H is actually indicating a power density in the direction of propagation. That's why it is called as a pointing vector. So P bar is called as E cross H, pointing vector. And we know this property very well, that P bar is perpendicular to E and H. Why? Because P is E cross H. So that's why it will be always perpendicular to the plane in which electric and magnetic field is. So this is what we have till now studied. It's the same thing, except that we are now giving a new name to E cross H. And that new name is the pointing vector. And we are giving this new name because of some valid reason. We are seeing that E cross H is nothing but it's a sort of power density. That's why we gave it as a name as pointing vector. Or in other words, this P bar, which is the pointing vector, it represents the instantaneous power density vector associated with the electromagnetic field at a given point. So it's a, sorry, this should be Py, pointing vector, Py. So this P bar is nothing but it's an instantaneous power density vector, also called as a pointing vector. And what it is giving you? It is giving you the instantaneous power density of our electromagnetic wave at a given point. At a given point. That means P bar is now a function of X, Y, Z, and also the time T. Because my electric field and magnetic field both are also a function of X, Y, Z, and time T. Okay. So now, once we have the power density, then you can easily get the power. How you can get the power? You can easily get the power by integrating it over any surface. If you see here, see the integration of the pointing vector over any surface will give us the net power flowing through that surface at any given time. So therefore, the instantaneous electromagnetic power through any given surface, and this surface is of area S, is given by the pointing vector. This is the instantaneous electromagnetic power is nothing but integral over S, the instantaneous power pointing vector, which is nothing but the instantaneous power density vector over ds. And what is P bar? Is E cross H dot ds. This is in watts. But again, this will only give you the instantaneous electromagnetic power. That is, it will give you the electromagnetic power only at an instant of time, which is not good for us, because we have seen from our background, say knowledge of electric circuits and electronic circuits. Whenever we are working with AC, it's better that we work with the average powers and the RMS powers. So here in our electromagnetic theory, it's better if we always go for an average power. So therefore, instead of instantaneous power, we always prefer to find the time averaged power, and hence we define the time average pointing vector, which is P average bar. How? By integrating the instantaneous power density vector P over the time of our electromagnetic wave, which is 2 pi over omega. And which is this one. This is very typical. This is coming from electric circuits. You can think it from the electric circuits point of view. So P average is 1 over T integral 0 to T P bar dt, which is when you do the simplifications, which, you know, I'm now skipping here. But if you want, you can go and look into your textbook. The simplifications are done. So when you do the simplification, you will get it as half time real part of ES cross HS conjugate. See, conjugate. This is important. It is conjugate. So it's not new, because if you find the average power in electric circuits also, this half will come. Half times VI. So here also half real part of ES cos HS conjugate. This is what you will see the average power. And now this average power density, power vector or average Poynting vector. Now, if you integrate it over any surface, then it will give you the time average power. The time average power. That is, the time average power is equal to integral over S P average vector over a surface ds is integral over S half times real part of ES cross HS conjugate ds. So this is how you can find the electromagnetic power which is crossing any surface because of my transverse electromagnetic wave. So first I will find the P average Poynting vector, and then from there I can find the time averaged power. Okay, so this is a very easy way of understanding, you know, that since E and H are coupled and since they are traveling in the same direction, we know E unit is volts per meter, H unit is amp per meter. So when we put them together, we are seeing that it is nothing but the power density. Okay, so let's take an example. So now this is an example where we are seeing that we have a uniform plane wave propagation and it's a lossless medium. So when it is, see guys, when the word lossless medium comes, you know, automatically we know that it is sigma is 0. And this is the epsilon R, this is the mu R. And the electric field is given by this. This is my electric field, which is given in the instantaneous form. So its component is in the x direction and it is traveling in the positive z direction, volts per meter. Now we need to calculate the electromagnetic power through a rectangular area of this 3 by 5 meters square, and which is located at z is equal to 6 meters. So if this is my z, so it is 6 meters and it is 3 centimeters, 5 centimeters. This is my surface area. So we need to find what will be the electromagnetic power which is crossing this rectangular area. So first, what we need to do, how to address this problem? First, because electric field is given to us, so our first thing is I will find the magnetic field, or I know the expression or the relationship between them. So in the present case, this is my electric field in the phasor form, because I want to work in phasor form. So therefore instantaneous form, I'm changing into the phasor form. So ES is AX10 e power minus J10Z. Now my first objective is to find the associated H. So how do you find associated H? Same, E bar cross H bar will give me the direction of propagation. So my direction of propagation is AZ. My electric field is along the AX direction. So my magnetic field will be AY direction. So that's why it is AY E naught over eta. This is eta, eta. So you can find eta. So here eta is 40 pi, which is root of mu over epsilon. So mu is known, epsilon is known. If you just put all those, say values, you will get 40 pi ohms. 10, e power minus j 10 z. And already lossless medium is given to me. So therefore, I'm not going to go and find the loss tangents and identify what type of material it is, because it is already given that it's lossless. Now, once I have this, once I have the electric field and the magnetic field expressions in the phasor form, then I will first find the average Poynting vector. So the average Poynting vector is given by half epsilon, half real part of ES cross HX conjugate. So I'm putting the E here, I'm putting the H here. So I'm finding the conjugate. So if conjugate, guys, again, remember in the complex number, conjugate means wherever is J, its sign will change. So it becomes now plus J 10Z, and AX cross AY is AZ. This is 100 over 40 pi. And this e power minus j 10z, e power plus j 10z, they will become 1. And this is my average Poynting vector, which is pointing in the z direction. Now, after this, you will just simplify it. This is my average Poynting vector, 0.398 AZ watts per meter square. Now we need to integrate it over the rectangular area. So if we integrate it over the rectangular area, so what I'm getting here, I'm getting it as 0.398 AZ times dx dy AZ. And if you integrate it, since our average Poynting vector is uniform, so therefore I do not need to do this integration. I can simply multiply it by its area, which is 3 multiplied by how much? 5. 5 3 is 15. So 5.97 watts. Okay. So this is how you can find the average timed power from the Poynting vector for our electromagnetic wave. Okay. So here you have one more example. And this example, you can check it at home, but there is just one thing which I wanted to highlight here. So it is saying that you have a uniform plane wave which is propagating in a lossy medium. So now is a lossy medium. And this is the electric field. And this is the associated magnetic field. And because it is a lossy medium, guys, that's why if you see here, I have this angle. Because this is the angle coming from the complex intrinsic media, intrinsic impedance. And we know H naught, E naught is related by the magnitude of eta, where theta n is the intrinsic impedance angle. And that's why you have this theta n, and H naught is here. So this is for the lossy media. Now, the question is, we need to find the average power, the average Poynting vector and the average power through a rectangular area, which is A cross B. And this is situated at X is equal to Z and parallel to the YZ plane. Okay. So it's in the YZ plane, but it's at a height X is equal to C. So how do you do that? In a similar manner, you will take the electric field, you will take the magnetic field, first find the time averaged power, the average Poynting vector. And if you see the average Poynting vector after simplification, you will see that this is my average Poynting vector. Okay, so you can look at the simplification. So here what I want to highlight is this. If you see here, This is what I want to highlight. Yes. So what is happening here? Okay, just let me put it here. Yes. So what is happening here? So if you see here, my electric field and magnetic field both are traveling in the positive z direction. Can you see here? So their propagation is in the plus z, plus x direction. So it's the plus x direction. It's in the plus x direction. But now, see, my magnetic field is attenuating as e power minus alpha x. My electric field is also attenuating so x direction. X direction means what? You have ax. So this is az. So this should be ay cross az. So ay. So when you look at these two electric field and magnetic field, we are seeing that the electric field amplitude and the magnetic field amplitude, they're attenuating as a function of e power minus alpha x. But the power, the averaged Poynting vector, it is saying that the power is attenuating as a function of e power minus 2 alpha x. That is, the power is going down double e power minus 2 alpha x. Okay, minus 2 alpha x. So this is what I wanted to highlight. So if the amplitudes are attenuating as e power minus alpha z, then the power will be attenuating at double the rate, which is e power minus 2 alpha. Okay, so once you get this, then you can put it in your expression to find the power over the rectangular area. Okay, and at x is equal to c, and then you do the integration and you will see that this is the time averaged power. And again, you can see it is attenuating as e power minus 2 alpha. This is what I wanted to highlight. Okay, so this is our electromagnetic power transmission, which is carried by our electromagnetic wave. So now in the next 2 classes or next 3 classes, we will now look at the following. If my electromagnetic wave comes and hit an interface, okay, because till now we looked at only the boundary conditions of electrostatics and the boundary conditions of magnetostatics, right? But now what I'm saying is, now we have an electromagnetic wave where we have the electric field and magnetic field both. Now when it comes and hits an interface, that means it moves from one medium to another medium. Then what will happen to the electromagnetic wave? That we will see in the next class, because there will be a change in the medium and the boundary condition applies. So these boundary conditions, what does these boundary conditions do to my electromagnetic wave? What it will do to the amplitude of my electromagnetic wave? So obviously, logically, if you think, there will be some transmission, there will be some reflection. So that we will see it in the next class. Okay, so we will stop our lecture here.